folks that you see right now, we've got a facilitator. That's Pete. He's the guy helping us with those technical things. You also see Kelly Reed, another professor down there, and then our presenter, Mike Corral. My name's Forrest Leisinger. So I'm the guy that's talking. I'm one of the engineering faculty at HAC. I teach the mechanical program. Kelly teaches in the electrical program. Mike has taught for us in the past. So we're really excited to have you guys here today. And we hope that you guys are excited to hear about some pretty cool engineering stuff. So Mike's busy getting his presentation ready to go. I'm just going to talk a little bit about our program and stuff like that. So I'm a mechanical engineer, taught at HAC for a while. Mechanical engineering is I'm sorry. You're here to hear about mechanical engineering. So I've worked in nuclear aviation and also education, and I work on a lot of stuff. I work on a lot of stuff at home. So, Mike, are you about ready to get started?
I am. Yeah, I'm good.
All right, excellent. So I'm going to pass it off to Mike now, and he's going to start his presentation. If you guys have any questions along the way, you can raise your hand at the end, and we can potentially ask some of your questions. All right. So thank you, and go ahead, Mike.
All right. Thanks, Forrest. Hello, everyone. My name's Mike Corral. I'm a mechanical engineer. It's been an awesome career for me. I've been doing this for about 30 years. So I think if you're in this session, you're interested in mechanical engineering. So my goal today is to take those of you that are interested in it and make you very interested in it. And those of you that might be on the fence considering some other stuff to say, hey, I think mechanical engineering is super cool. So I'm going to go in that direction. So my goal is to convert some of you and not lose any of you. So those are my goals. I'm going to share my screen because I have a presentation. So I'll go ahead and do that. Okay, can everybody see that? Are we good?
We got it.
All right, awesome.
You can see it, Mike.
Yeah, my teenage children just wince in pain every time I'm clicking on things. So what I'm going to do is I'm going to talk about my experience becoming a mechanical engineer, and then I'm going to talk about the profession itself. So I'm going to go over, what you can expect when you're working as a mechanical engineer, what you can expect to make as far as money, what the curriculum is like when you go through an engineering program. And then we'll kind of work a fun engineering problem just so you can see how applied mechanical engineering works. So this is my background. I have a Bachelor of Science in Mechanical Engineering. I went to West Virginia University for that. And then, I continued at Penn State Harrisburg. So I have a Master's of Business Administration and a Master's of Engineering Science. So a lot of times you'll hear people say engineers are lifelong learners. Once I started going to school, I kind of realized there's not much on television worth watching, and I got kind of bored. So I just kept going to school while I was working. I didn't take a direct path into engineering school. I went to Dauphin County Vo-Tech. I wasn't a great high school student, but I always loved to draw things. So I got a job. I worked kind of in machine design and die design for a period of time. And I started working with engineers. And when I started working with engineers, I was like, this seems really cool. Like, to be able to apply science to design is something that interests me. So I did go back to school at night. I went to HAC for several semesters to get on proper footing to go back and get my undergraduate degree. So if you're creative and you really like to draw, like to design things, I would encourage you to figure out the math. It's important, but you can do that because if you're into designing, you're already operating in a pretty logical way. So when I graduated, I went to Armstrong in Lancaster. They make floor tile, ceiling tile, building industry products. I was a project engineer there. That was a lot of work on really big equipment. So I did that for 3 years. I was managing projects and managing teams. After 3 years, I decided I didn't like that type of work. So I wanted to get more into the technical side of engineering. So I went to TE Connectivity, which was AMP at the time. And I went in as a manufacturing engineer. So I was in manufacturing at Armstrong. I went to manufacturing at Tyco. And I worked in a plant, supported plant operations for a couple of years, but again, wanted to get more into the technical side of engineering. So I moved into manufacturing development. So I was an engineer that developed processes for new products. And after doing that for a while, again, wanting to get more technical, I went into product development and started designing and developing products. So that was about 25 years ago. I was at TE for 7 years, and then Phoenix Contact, which is right down the street, was opening or starting their own development organization. So I went there as a product development engineer, designed and developed the first product that was developed in the US. Phoenix Contact is a German company, privately owned. All of their development engineering was previously in Germany. So it was a really small development organization when I started. So I came in as one of the first product development engineers. And as we grew, I hired a team. So I became the group leader for the product development group. I grew that to about 7 people. And then I took on development engineering and manufacturing engineering as a manager. So I grew that group from about 3 to 7 people. I wound up with 14 direct reports. Working as a group leader in product development and manufacturing engineering. And then I became a senior product development manager, where I managed the whole development group at Phoenix Contact. I was there 14 years. Great company. They're in Middletown. They do hire interns. So if you go to school locally, I would reach out to them. Really good experience, really good company. So I've always kind of wanted to work for myself and do an entrepreneurial effort. So I left Phoenix about 2 years ago, and I'm now at a co-working space in Lancaster City, designing and developing my own products. What you're seeing behind me is marketing materials and my production organization, which is just me in an office. So I'm living that life as an entrepreneur right now. I'm trying to get my first product off the ground. So if there's one takeaway from this slide is, if you get an engineering degree and go into a company, and you kind of see, okay, I've started my career, but I want to go maybe in a different direction, or, kind of plot to an end that makes sense to me strategically. Engineering degree is always a good thing to have because you're super flexible. You can pick up on the experience you have, you can build on it, and you can go in whatever direction you desire as long as you put forth the effort. So I think in looking at this, what I want you to understand is with an engineering degree, you do have a lot of flexibility. So I'm going to go over what mechanical engineers do. This is changing a little bit as the times are changing, but it's super good time to be a mechanical engineer. So really, it's very broad. So in mechanical engineering, you get a little bit of electrical engineering, a little bit of industrial, a little bit of business. So it's one of the broadest engineering disciplines. And really what you do is research, design, develop, test, and manufacture. I mean, that's what I've done my whole career. If you look at a common skill set, modeling, simulation, computer-aided design is huge in mechanical engineering, and so is computer-aided manufacturing. If you look at this picture, that's a typical workstation. It's just two monitors. I don't know why electrical engineers usually have 3 or 4. I always would kind of poke fun at them for that. But MEs typically have 2. Casual dress typically, you can't come to work in rags, but, I think that, nice pair of jeans, sweater, whatever. I mean, it's kind of office casual. I don't know how many jobs are remote right now. COVID has shifted everything. So I think a lot of things are remote. I will say that, office spaces have become open the last couple of years. So you used to be in a real tight cubicle. There seems to be an emphasis on collaboration in engineering. So open office spaces, I think, are a lot more common. And it's pretty casual dress, but if you're making a presentation or you're, a customer coming in, it's not uncommon for the policy to be, hey, don't wear jeans that day. Like put it together, look buttoned up. And that depends on the company. But the types of jobs that you can have as a mechanical engineer, these pictures I think are a really good description. The upper left is a jet engine. that really shows simulation. So that's all of mechanical engineering. It is stress and strain, it is thermal behavior, it is thermal management, it is the dynamic load, it has air going through it, so computational fluid dynamics. You won't do all of that, you'll probably specialize, but that simulation is a big part of mechanical engineering. And the picture on the right, of making drawings, checking drawings, measuring parts, that's a big part of it. If you're in product development, you're going to develop those types of skills. And that little thing, that calculator, we still use those all the time. You won't use your phone. You'll have a pretty tricked out calculator by the end of a engineering curriculum. So factory automation is huge. As we grow our manufacturing footprint in the US, it'll largely be automated. And mechanical engineers design machines, program robots, understand production flow. It's a big thing that they do. So that'll be a big part of the future. We'll talk about that a little bit later. And, power generation, the picture that you're seeing there is a natural gas power plant. We're really moving from coal to natural gas. We're going to solar as well, but solar is super inefficient to get on the grid. So it's mostly natural gas. If you're going to make power, you're going to generate steam, you're going to generate heat. And if you generate heat, mechanical engineers do a lot of study in thermodynamics and heat transfer. And the lower one, the little kind of bulbs that are on the ground, that's pressure vessels. I have a friend in San Diego that designs pressure vessels for a living, and he's a mechanical engineer with an engineering license. So pressure vessels, if they're not designed right, can come apart. They can explode. They can let all their pressure out at once. So if you're going to design one of those, an engineer is going to do it. If none of that really seems interesting to you, I have some friends that work in technical sales. So the picture on the lower right, if you're selling a technical product, it needs to oftentimes be sold from an engineer to an engineer. It's just very typical. I would say at TE Connectivity and at Phoenix Contact, a lot of our salespeople had engineering degrees. So if you're a social butterfly but love engineering, if you want to go out and talk to people, travel a lot, have dinner with people you don't know on a regular basis, maybe play some golf, those are a little stereotypical, but that's what salespeople do. And, we need engineers as salespeople as well. It's super important going forward. So those are really the types of careers in mechanical engineering. I think it's important to look at where mechanical engineers are employed. So in the US, 2019, they publish this data maybe every 5 years, the US Department of Labor. So right now there are 316,000 mechanical engineers in the US as of 2019, and the anticipated growth rate is 4% over the next 10 years. So a 10-year projection is super hard to make. I think it's going to be more than that, but that's their projection right now. And if you look at the industries in which mechanical engineers work, it's manufacturing and production. Talked a little bit about that. And then professional, scientific, and technical services. So if you look at those, one is, factory automation, working in production, doing production support, designing machinery, production infrastructure. The professional and scientific is more the analysis stuff. Like think back to the jet engine, doing fluid dynamics, finite element analysis, stress analysis. So those are the two major chunks of what mechanical engineers do. It tails off pretty quickly from there. So government, waste management, wholesale trade, construction, those are a piece of it as well. I think that it's interesting that the construction is so low in mechanical engineering. Mechanical engineers oftentimes will do heating, ventilating, and air conditioning systems in buildings. That can fall to civil engineers as well, because civil engineers can do the structural part of it. So it's not a very big segment. If you look at maybe the trends, I'm trying to read what the trends are here. I've been doing this presentation for a while. So in 2014, the projections were that we would have 137,000 people in manufacturing, and their projection was off. So it's much bigger. It's 151,000. And the professional and technical services has outperformed as well. So it was supposed to be 87,000 and it's 90.7. And the 2029 projection is these are both going to grow. And I think they have it spot on because they have manufacturing growing more than the professional and technical. So, if you're watching the news, you see what's going on in popular culture right now. Supply chain issues are a big thing. Importing products that are produced outside of the US has become problematic. I think consumers are spending their money a little bit differently and will pay a little bit more to get US manufactured goods. And we do have a tariff system in place right now with Asia, with China, that has helped. So I think that's all good for mechanical engineering. As more things are produced in the United States, it's better that things will be, again, further designed here, which has always pretty much been the case. But having them produced here is good for the mechanical engineering careers. And if you look at out of that 7.7 and 3.6% growth, what's the breakdown? This speaks to my previous statement, which is, machinery and manufacturing is going to be the biggest growth area. Transportation, equipment, motor parts, vehicle manufacturing, that's a big thing in the US. Cars, I think, have been tariffed for a long time. So all the big car makers are here. Toyota's here, Honda's here. I think Hyundai is here. Mercedes-Benz, BMW, they're all producing in the United States. That's good for mechanical engineering. And it's good for, just local production of parts. If you're going to build a car, you got to make a lot of parts. And there are a lot of companies in the United States that do that to produce, to support the US auto industry. So let's talk a little bit about your education options. So there are two-year options that you can take. One is to get an associate's degree in mechanical engineering technology. It's a little less math heavy, a little more practical. And when you're done with that, you can get a job. So you can just go and get a job. When I was at Phoenix Contact, I think we hired in my team alone, we hired 3 hack graduates that have 2-year degrees in MET. One of them designs all the tooling and production, and the other one does design work and supporting the engineers in development. So really good folks, great at what they do. The other option is to get an associate's in science, which is designed to transfer to a 4-year school to get your bachelor's degree. So those are kind of the two out of the gate options. You can transfer those credits. Again, this is good. Engineering degree is always a good thing to have because you can use those credits to go forward for your 4-year degree. So with the MET, you can get a BS MET. I think that's offered at Penn State and several other schools. If you get the associate in science, you can get a BSME, and that's at Penn State as well. You can also go to a 4-year school. Don't have to go to Hack. You can go to a 4-year school and get an engineering degree. The technology degree in the MET is, again, a little bit more practical. The BSME is a little more science-based. I've worked with both engineers with both degrees throughout my career. I have not seen a functional difference in them. I will say if you're going to go to graduate school, I would do the BSME because if you do the MET, I think you have to take 2 classes before you would start graduate school. So if you're going to do it, I would do the BSME. But those are really good options. And then I'll say the popular paths in graduate study, are an MS in mechanical engineering. It's common to kind of kick in that direction if you want to get more specialized. I got my master's degree in engineering just because I wanted to understand more about the problems I was solving. I didn't have some motive that I wanted a particular job or I wanted to gain more money. I just wanted to gain more knowledge. But an MS or an MN is typical. And then the other typical is an MBA. When you work in engineering, you'll work in business, and you'll always be expected to either make or save your salary every year for the company. And somebody told me that the first year I was working, and I was like, oh my gosh, that sounds so arduous. I don't know if I'll be able to do that. I can tell you, once you're an experienced engineer, you will make or save 10 times your salary every year for your company. It's not, you're going to be a problem solver. You're going to look at problems, they're going to be given to you, you're going to solve them. And as you solve them, you're going to achieve that, and you're going to achieve a lot more than that. But the only reason I say that is because business is a part of it. You will talk about dollar signs a lot in your engineering career because you're trying to make the company profitable. And along those lines, these are the salary ranges that you can see at the different education levels. So these, I think, are based on 2019. And they're like mid-career stuff. It's not fresh out of the gate. And you can make more than this, you can make less than this. And you also have to be careful. It depends on where you live. You know, it's hard to live in San Francisco on $130,000 a year. So the maximum number is not livable in San Francisco. So this is data for the whole country. You have to take the cost of living in the area that you're in into account. But you can't be motivated by money. I mean, it can be a piece of it. But I would say, you know, I like solving engineering problems. It's really cool stuff. I like getting up in the morning knowing I'm going to do that during the day. So it's I think that has to be a little bit bigger part of the motivating factor than the money. So let's talk a little bit about curriculum. So this is a typical undergraduate curriculum for mechanical engineering. So, you know, you typically start out with core sciences. So calculus, chemistry, physics, and English. Ouch. It sounds a little bit like high school if you're in AP classes. But, you know, your freshman year, you know, at least freshman year, it's really, really hard. It's a real concentration on these rudimentary sciences, and it does continue into your sophomore year, just because there's so much information there. So when you get into, I'll say, the back half of your first year and your whole second year, you'll start to get into the engineering fundamentals, like fundamental classes. So in mechanical, you know, you'll have some group activity, intro to engineering stuff, but you'll also get into static structures or statics. So that's the study of forces on things that aren't moving. So if you sit on a chair, how much force is the chair exerting into the ground through the legs? That's statics problem. Super fun stuff. It's pretty math and geometry dependent. And then you'll do dynamics. So dynamics is if you kind of slide the chair across the floor with some initial velocity, how far is it going to slide until it stops? It's a lot like statics, a little more complicated because it has acceleration and a time element in it. So the math gets a little more complicated. And then one of my favorite classes to this day is strength of materials. So if you sit on the chair, how big do you have to be to break the chair? You know, at what point is it going to break and how is it going to break? This is the coolest thing in the world to me. I've always broken things my whole life, much to the frustration of my parents. And then I got to college and realized there's a whole science around how things come apart and how they break and how they fail and how to design them so they don't fail. So that's a really cool class. It's usually combined with a lab where you go in and you break stuff and write reports on it. So, you know, that's really kind of the rudimentary part of engineering that you'll get in the first 2 years. It's a lot in the first 2 years. And I will say, if you work really, really hard in those years and learn the actual science and the theory behind everything, your next 2 years are going to be a lot more pleasurable. Because engineering does keep repeating itself. These themes that you learn in the first 2 years, you will use those tools in the last 2 years, just on bigger problems. So, you know, I would encourage you to kind of get through those first 2 years, learn the material, learn it really well. And the last two are, forgive me for saying, but I thought they were kind of fun. So, you know, in your last 2 years, you'll do something in mechanical design, typically with analysis in it. You'll get into some advanced classes, you know, kinematics, which is the operation of machinery, vibration analysis, which I thought was super cool. And then I'll say the fluids and heat transfer part of it, you know, fluid mechanics, thermodynamics, and heat transfer. And then you'll usually have a senior capstone where you apply everything. I will say most mechanical engineers will gravitate to the strength of materials like I did, or the fluids and heat transfer. But most new graduates that I hired at Phoenix were good at both. And I never really worked the muscle of using my fluids and heat transfer stuff, but I always made new hires do that, and they stayed really good at both. And, you know, thermal analysis in the types of products that we designed at Phoenix was important. So it's not to mean you won't be good at both, but I'm much stronger at the mechanics part of it. There could be a chance you need a professional engineering license. So, you know, if public safety is at issue and there are local codes that you have to comply with, like when you build a building, then you will need a professional engineering license. I've never needed it in product design because there's so much risk to consumers in product design that I don't do the final testing and certification. That's done by an outside company. So if you look at the back of your phone, you might see like UL, CSA, CE, IEC, EX. These are outside companies. Those products are tested by somebody other than the company that designs them to make sure no one gets hurt. So that's the reason that I don't have a professional engineering license. It doesn't have much applicability in product design because there's so much risk involved. So there are a couple paths to a professional engineering license. You can get it if you have a 2-year degree. And you can get it if you have a 4-year degree. So if you have a 4-year degree from an ABET accredited school, you can take a fundamentals of engineering exam. You qualify. And I took mine, I think a month before I graduated. It's an 8-hour test. It's kind of like multiple choice in the morning and big problems in the afternoon. I took a cold. I didn't study for it because all that information was fresh in my head. Having just finished my undergrad, I passed it. And then, after 4 years, you have to work with other professional engineers. And then if they write a recommendation, you can sit for the professional engineering exam. So I didn't do that. I don't work with professional engineers. They're not really in my industry. So if you have an associate's degree, it's the same rules, but you have to work for 8 years before you sit for the PE exam. And then it's the same rules of working another 4, before you sit for the fundamentals of engineering. And then you have to wait another 4 years until you sit for the professional engineering. So that is the path to get licensed. And I'm going to work through an engineering problem with you. So my son is a skater, so he likes to skate. He'd be embarrassed by his picture because he's a lot older than this now, but I was a skater when I was growing up. So we're talking 70s, like back in the infancy of the sport. So I can't do very many cool tricks, but I thought it would be fun for him and I to build a quarter pipe. So we built this quarter pipe one afternoon, and, my wife left and said, don't hurt yourself. And I said, trust me, I'm not going to do any of my old tricks or ride the ramp. I have no interest in breaking a bone. So we had the ramp built for 5 minutes, and I immediately took a skateboard and started riding the ramp. And I was doing all the tricks that I could do in the 70s. And it was awesome. I didn't have any mishaps, didn't fall, didn't break anything. But about a week later, I went out to tell my son to put the ramp away. There were wheels on it so we can roll it out of the way. It was going to rain, dark clouds everywhere. I went out to say, dude, you got to put this ramp away. It's not painted. It's going to be a mess if you don't. And the ramp was on our driveway, and I jumped on our driveway on his board and just took a push and started rolling across the driveway. And he had a piece of wood across a little dip at the entrance to the driveway, so he could enter from the street before he went on the ramp. And I took a push, and I was kind of barking at him saying, dude, come on, help me get this ramp. And my body was turned away from where I was looking. And I hit a little pebble on the driveway, and I didn't have enough inertia to get over the pebble. So the board stopped, and I chucked myself right onto that board, knee first. So this was kind of the accident. I tried to pretend I wasn't hurt until the next morning when I couldn't get out of bed. Went to the doctor and realized I broke my kneecap. So I kind of went to the doctor, got that all taken care of. I was sitting around the next weekend, and I was bummed because I couldn't do much of anything. I was sitting at the kitchen counter with my knee wrapped. I was like, I'm bored. I don't know what to do. And there was a bunch of paper there, calculator, pencil. I was like, I wonder how much force I put on my knee when I hit that board, because I cracked my patella. So I just started playing around with some numbers, and I'm like, okay, I know my weight. I know the height of my kneecap. Let's figure out how fast my kneecap was going when I hit the board. Let's start with that. So I just used work energy. This is dynamics. This is, second year stuff that you would do. So I was going about 1 foot per second horizontally. My kneecap sped up to about 10.5 feet per second vertically. So I accelerated. I sped up quite a bit. And then I know the geometry of that board. So I can just look at this as a simply supported beam. This is a little bit of statics and strength of materials. I know what type of material and what the geometry of that beam was, that little board. So what I did is I just threw 1,000-pound weight on this to get a stiffness. Engineers talk in stiffness all the time, mechanical and structural engineers. So it looks like about 16,300 pounds per foot, super stiff beam, right? If you pushed with that much, you would break it, but it's not that springy. It's really stiff. Everything has a stiffness and a spring rate. I got pulled over once for a speeding ticket on the South Bridge in Harrisburg. I couldn't believe how much my car was jumping up and down when trucks went past. So even though that big bridge looks infinitely stiff, it's not. It's springy. It actually has a stiffness to it. So what I wanted to do is figure out, okay, I know a couple of things about that now. I know a spring rate of that board, and I know two things about it. I know my knee was moving 10.4 feet per second when I hit the board, and I know my knee was moving 0 feet per second when it stopped. So what I wanted to do is just figure out how far I compressed that spring. So I can go back into the work energy equation, and I can say, okay, I think I actually compressed that 0.18 feet. I don't feel quite right, but let's go into Hooke's law and use the equation for stiffness and back out how much force that would be. So wow, 2,900 pounds. Like, that's quite a bit. Didn't feel quite right, felt a little high. I was thinking maybe 600, maybe 700. So this is very typical in engineering. You do all this work and you do a calculation, you ask your colleagues, does this feel right? Like, check my math. Does this look right? Check my application of the science. So what I did is I said, okay, let's just calculate this problem again, not using any of the information from the previous page. I love strength of materials. I know that I broke my kneecap, and I know the size of the fracture because the doctor friend of mine that looked at the x-ray with me kind of made fun of me while he was measuring the size of the crack. So I know the size of a human patella. Somebody loaded the dimensions of 92 adult patellas on the web, which is awesome. I think that's why the web exists. So I could figure out the geometry and the cross-section of that crack using the measurement that was taken in the doctor's office and just the general knowledge of the shape of the patella. And since I know the size of that crack, I know from strength of materials what the relationship is between the strength of the bone and the cross-sectional area and its associated force. So since I know that cross-section, also on the internet, I can find the ultimate shear strength of human bone. So at what point is bone going to start to come apart? And if I plug that calculation in to what I know from strength of materials, I got a very similar answer of 2,800 pounds. So I was like, wow, I think my assumptions were close enough on the previous page that they kind of back out given the size of this crack. And I was so excited that I got, very close to the same two answers. I called my wife from upstairs. I'm like, you got to come look at this. Look at how much force I put on my kneecap when I broke it. And she's like, and this matters why? Like, why would you spend all this time doing this? You're been married 25 years. You're still like the weirdest person I know. But it was just kind of fun to do the calculation. And these are, just examples. If you go back here, I mean, this is all stuff that you would learn, I'll say second year in mechanical engineering. It's just application, and no matter what you do in really, really cool analysis, in computer and in simulation, it all starts with this kind of fundamental understanding of what you think the answer should be. Computer programs now they're pretty robust. Like, you can put in bad information and get an answer. In the infancy of analysis in computers, the computers were super picky. So if you put in, say, material properties or something that didn't make sense, the whole system would just crash on you and lock up. That's gone away. So a lot of times when we do an analysis in the engineering world, we start with some hand calculations to figure out, where should we be? Where's our ballpark? And then we should be able to explain the difference between the simulation and the hand calculation. So, if you look at what's going on in mechanical engineering, this is really all the cool kind of product development stuff. So, I have simulation packages in my business. I can do impact testing. Drop testing of something that you ship is a big deal, especially in consumer goods. At Phoenix Contact, we had to drop things 3 times on the same spot from a meter, and they still had to work and not break. And there's a lot going on there. I mean, everybody drops their phones. Dropping your phone without a case on it is super dicey. But with the cases, they do really, really well. You can do strength testing. I'm a biker, so this is just a crank at the bottom bracket to look at the stress and deflection behavior. Plastics flow. I do a lot of plastic part design, so you can simulate how the flow is going to enter into a part and fill and give you part quality. And then the fluid flow stuff is really mathy. If you look at simulating flow, like through a turbine on the right, we're doing computational fluid dynamics for airflow inside an electronic housing. I know with the heating of electronics, we did a lot of that at Phoenix Contact. It took us about 3 years to get good at running those analyses and getting the right answer. We could simulate, depending on the position of an electronic product, whether or not it's going to exceed the rated chip temperatures. If you look at any electronics or any printed circuit board and you look at all those chips on it, every one of those chips will operate differently cold than it does at ambient, than it does at hot. And, if you've ever been out running in the cold and your iPhone stops working, it's because it got too cold. If you've ever been using your GPS and, your phone is on dashboard and it's just cooking in the sun, sometimes it could quit. It's because the electronics are not behaving the same way at cold and hot. So, we did do simulations to predict how hot chips are going to get before we even build anything. So, that saves a lot of money, saves a lot of time, and it's mechanical engineering stuff, like through and through. And I think in your careers as engineers, that's going to get bigger and bigger, and we're generally accepted and more. Just people are learning more about it all the time. So those are the types of things that you can do in mechanical engineering. It's likely what'll be done. And I just think there's so much cool stuff going on right now mechanically. I really like what Tesla's doing in general. I think their SpaceX stuff is fantastic. I went and saw Tesla at the King of Prussia Mall, where they had the whole body off the car. And it's like, wow, there's not much to this mechanically. This is going to be revolutionary if we can ever get the batteries to work. Boston Scientific is doing the kind of scary robots that do backflips and gymnastics routines. Reminds me of Terminator, so I find it a little frightening, but that's all mechanical engineering. Self-driving cars are awesome. I'm a mechanical engineer that doesn't like to drive that much, so I feel like it's wasted time. So I'm looking forward to self-driving cars. And production and manufacturing is going to be, I think, significant in the United States throughout the span of your careers. So I think there's really exciting stuff happening. I like mechanical engineering the most because you're working on tangible things. You're working on things that you can physically pick up, and show people and that people use and that aren't in the ether. And that's not to make a slight at software or electrical engineers. I've worked with them my whole career. I'm humbled by what they do. You'll work with other engineers throughout your whole career, and watching what they have to do to get something to work with firmware on it is humbling. It's very, very challenging, cool job as well. And you'll work with those people a lot. So that's all I have. It's awesome to talk to everybody. Super exciting time to be an ME. Excuse me.
All right. Well, thank you very much, Mike. So we have time for some questions. If anybody wants to put questions in the chat for Mike, myself, or for Kelly, we can try and answer them for you real quick before the next session. Biggest misconception about mechanical. Do you want to try it or do you want me to take it? Mike, what do you think?
Biggest misconception. That's an interesting one. I don't have much Forrest. I mean, maybe that we just use wrenches and,
Yeah.
work on cars. I think that's
Yeah,
maybe,
I would kind of go with that.
yeah.
Mechanicals end up anywhere because just about every interface that you have with the world involves some kind of mechanics. So that's it's not just cars, and there's lots of industries lots of industries with mechanical engineers. Anybody else with a question? Okay, so the benefit of specializing when you can get an associate's. So the question is, and I'll read these off because you guys might not see these. What's the benefit of specializing in engineering when you can get an associate's degree and land a job? Well, I would say that if you pick any of the big four, which would be mechanical, electrical, civil, or chemical, that's not really a specialization as much as it is a direction. So we have engineering transfer, but that is set up to transfer to one of those disciplines at a 4-year school to finish. So that can create some confusion. In general, you need some kind of speciality in order. Well, so for example, my first industry job, we hired. They didn't care what you were because they had spots for mechanical, electrical, civil, or chemical engineers. And the company basically looked at it like, okay, well, we're getting someone that's technically competent. We can bring them in and train them in what we do. That's common in larger companies. A lot of times big companies will have rotation programs, and you'll meet all the other new hires, like when they bring in a class of new engineers right out of school, and they'll kind of rotate you around through the different disciplines. In general, with just a 2-year degree, like our 2 years degrees actually have more of a technical focus. Our 2-year degrees actually have more of a technical focus. So you get more technical content with the technology 2-year degree as opposed to the straight engineering 2-year degree. Hopefully that answers your question. And I hope I didn't just make you more confused. Anybody else? Sure. I'll tell you about a project I worked on. I'll go quick. I worked on integrated electronic engine control for Lycoming engines. That's currently flying in a bunch of aircraft, and I just went back up to visit and looked at a bunch of the stuff that I did for that program, more than a decade ago. I'm pretty proud of that. I got about 5 patents out of it, so that's a good one for me. Mike, did you want to?
Sorry, what was the question?
The question is, can you talk a little bit about some projects you've worked on in the past and what you're proud of?
When I was initially hired at Phoenix, they hadn't designed a product outside of Germany. So we designed a new wiring interface module that's completely modular. So it was a completely different way to do things. It's all still produced right in Middletown at Phoenix Contact. So I did the whole product design. I was a department of one at the time. We got 7 patents on that product. We could make the product a lot more cheaply and in an automated way. So it's all put together with automatic assembly right there in Middletown. So it's a good product. It's had several product extensions. It's grown over the last 15 years. And we probably created, I don't know, 7 or 8 jobs here locally to support the creation of that product. So that one was a long, hard project, but it had a really good result. So I think that's typical in your life. The longer and harder it is, sometimes the more you appreciate it later.
Yeah, I will say so. I did work in development. A lot of the stuff that I worked on, we would get a full prototype done. We would sell like 20 units, and then that project would end, and you wouldn't hear anything else about it. So, and also some of that was for military stuff.
Mm-hmm.
So they wouldn't necessarily tell you if they had plans for more than 20 units. Any other questions?
I saw a question here typed in the Q&A of just what's your favorite part of engineering? I would say, even though I'm introverted like most engineers, I really I like people. I like working with people. I mean, when you work in engineering, you work with people in marketing, people in other engineering disciplines. It's just I really like just working with a lot of different people. In manufacturing and production, and in marketing and the other engineering disciplines.
Okay, so my favorite part, I just saw it. Sorry. Some of you folks are in the chat, which I think I told you to type in, and there's also a Q&A. So I just found that button. So my favorite part is basically solving and creating stuff. There's nothing like, with 3D printers now, you guys probably have some of it at school, but when that technology was a little bit more rare, it was like Christmas when the first prints would show up in a box or the first 3D printed parts that you were making for a product. So, that was super cool. Also, some of the times when it's like 10 o'clock on a Friday night and you're trying to get something shipped out and everybody is working as a team trying to get the last part of an engine put together, that's pretty darn cool. So those were some of my favorite parts. Another one in there is, do mechanical engineers ever do the testing of products? And maybe Mike took that one earlier, but in my experience, sort of. So we had a bunch of product development engineers, and they supervised and watched the tests. I worked at a company that had a union for hourly workers. So they had a lot of the technicians were in the union. So the technicians would actually perform stuff, and the engineers would collect the data and watch what was going on. Now that was engine design. So the engineers were in the dyno cells right beside, or the dyno cell control rooms right beside the guys actually pulling the levers and doing stuff, collecting all the data. So they got to be there when things blew up or shoot across the room or caught on fire.
Yeah, I'd say in my experience, the engineers do a lot of testing. There are 2 different types of engineering tests in product development as I know it. There's what we call verification testing, which is you've got your prototypes, you're playing with them, you're doing all the testing. That's usually done by the engineers because you learn a lot about your design doing that. But then the qualification testing, which is the company saying this is now ready to ship, that is done by somebody else. We have an unintended bias for our designs. We want them to pass testing. So you really need somebody who doesn't have any emotional connection to the product or the design to do the final test before you release it to the market. But in product development, do a lot of testing.
Yeah, I did a RFI test once. I was building a Faraday cage, which is actually an electrical thing, which is the next presentation. So some of you guys are going to that. A bunch of us are going to be popping over into there momentarily. So we probably won't take any more questions at this point. But that testing Mike was talking about is very expensive because you're contracting an outside company. So we had 3 different versions of this. And when we got them all shipped and we wanted to figure out which ones we wanted to spend thousands of more dollars to test, So I put them together in my cubicle, stuck my cell phone inside it, and called from my desk phone. And if the cell phone rang, I knew we didn't need to test it. What do you think potential engineers, this will be our last question because we gotta go to the next one. What do you think potential engineers should know before getting into the field? It's a rewarding field. You do have to work hard. You have to study hard in school. A lot of times, especially depending on who your friends are in school, engineers get a little bit of a chip on their shoulder because we work hard on everything. And some of the other folks, especially depending on what they're studying, might roll out of bed at 2:00 in the afternoon and take 3 classes and then go back. Engineering classes are usually all different times and you have a lot of labs. The benefit, one other thing is you don't have to be a math whiz. So you need to be able to tolerate and understand the math. But the wonderful thing about engineering is, like Mike's demonstration, there was a lot of math in there, enough that it might be a little bit concerning to some of you. But when you are solving stuff in math class, probably about 70 to 80% of the time, it is just numbers on a page and it doesn't mean anything. The wonderful thing about engineering is all of those numbers mean something. So if you like to build stuff, if you like to build, Legos, Fords, motorcycles, all of that stuff, and you can think and see and understand how forces interact on stuff and know how much thicker to make parts of it, you're in the right place. The math will come with the understanding that you already have. So don't let the math entirely scare you. All right. All right. Well, we have to get our next presenter ready for 6 minutes from now. So I think at this point, I'm going to say goodbye. And it was wonderful having you guys. We hope to see you in the next presentation, unless you pick the other one. And thank you very much for coming out and checking out HACC and some of what we have to offer.